Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you, and this is the DADM 1 lecture and this is the 7th lecture. As you know, this is the course of 30 hours which will be spread over 12 weeks. Each week we have 5 lectures, each lecture being of 30 minutes. So, if you remember in the last lecture, which was the 6th one, we were discussing the concept of Bayes theorem. And I did mention that how the concept of Bayes theorem could be understood. So, Bayes theorem is basically coming from the actual background being conditional distribution or conditional probability, whatever you want to say. So, with condition and probability we went to the concept of Bayes theorem. Now, rather than basically going through the equation, I basically drew a neat diagram, explain that how if the overall universal set is broken down by n number of mutually exclusive and exhaustive events being given from by B1 to Bn, and then we can actually have an event A which is basically a conglomeration of some intersection of B's, such that we can find out the probability of Bj, j being from 1 to n. So, all those n's which were basically mutually exclusive and exhaustive, we can find out the probability of Bj's provided A has already occurred. And it can be extended into the second stage, third stage. By the word of second stage, third stage means and they are different type of combinations from one stage to the other. That means given B you want to find A, given A you want to find out C, given C you want to find out D, and so on and so forth. Now, let us consider a very simple example Bayes theorem, and then I will try to build up more such conceptual problems which can be solved using the Bayes theorem. So, the problem is like this: in an examination each question has 4 alternatives. So, it can be more than 4 also, less than 4 also, but for our problem we have 4 alternatives, of which only one is correct. Now, the problem again can be extended with more than one is correct, multiple choice questions, but let us keep it simple. So, if a student knows the correct alternative, then he or she is definitely able to identify it, otherwise he or she picks one of the alternatives at random. So, we will consider some probability distribution of probability values of picking the random answer, and there would be a simple concept, very simple practical concept for that also. Now, given that a student has identified the correct alternative, we are and what is the conditional probability that we are required to find out. So, what is the conditional probability that he or she knew the answer, assuming 70% of the students know the correct alternative to the question under consideration. So, now with this, what are the assumptions we will consider and how we will proceed. So, let me come to the problem directly, and it is a very simple one. So, let us define the following concepts. So, what are those as assumptions? Let us consider A suffix 1 or A1 be the event that the student identifies the correct alternative, B1 and B2 which are technically the mutually exclusive and exhaustive set. Try to remember the diagram which I had drawn on the fag end of the 6th class. So, B1 and B2 are the mutually exclusive and exhaustive. So, B1 denotes the student knows the correct alternative, B2 denotes the student does not know the alternative, correct alternative. So, what are the corresponding probabilities? Let us answer it very simply. Then we know if the student knows the correct alternative, it is given by 70% as in the question. So, it is 0.7, and the complement set of that is the student does not know the alternative is 0.3, which is 30%. Now, what are the scenarios? Given the student knows the correct alternative, and if A is the event, then the student A1 is the event the student identifies the correct alternative. Obviously, if he knows it, he will answer it correctly, hence the probability is 1. So, probability of PA or PA1 given B1, the answer is 1. Now, let us come to the second information. Now, if the student does not know the alternative, that means he is not sure. So, if he is not sure, in front of him he has 4 alternatives. So, the probability of answering any one of them is basically 1/4. Hence, the probability of A, that means answering the correct alternative by the student, provided he or she was not aware of the alternatives, is given by 1/4, which is 0.25. So, if this is the case, now we will try to answer the question what is required. The answer required is the probability that the student knows the correct alternative, provided he has identified the correct alternative. We will just formulate it as a simple Bayes theorem given the problem and solve it. So, the actual so this is what we want to find. So, this A, if you remember, I am going to this diagram. So, these are the B1, B2, B3, and I want to basically have A. So, this is A. I want to find out the probability of A. So, obviously, I will use the highlighter, use the yellow color. Let me use the green color, it will be, or the blue, it will be easy. So, I want to find out this probability, then this probability. I am going to add them up. So, what I am marking? I want to find out this probability, I want to find out this probability, I want to find out this probability. So, if you remember, for A, let me use the black. So, this one, this probability of A, if you basically go through it, is basically the sum of this, 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 this and this. So, this can be found out, put into the value, and the answer comes out to be 0.9032. I am not solving them, but I am trying to give you a pictorial diagram and you can understand it much better. An exercise which I would love the students to do. Okay, remember one thing, as we have started now, there would be many exercises which come up as we are discussing. These exercises are not part and parcel of the assignment, not and part and parcel of the end semester also. But please solve them, try to understand, because as we are going through the concepts, you will understand that how they would make some sense based on the fact that we had covered one concept, we will solve one small problem and then we immediately come up with the small exercise so that you can understand it very clearly. The problems I am telling you beforehand are very simple, easy, understand the concept and solve them. So, the exercise or the example is like this. The marketing manager of a toy manufacturing company is considering the marketing of a new toy. In the past, 40% of the toys introduced by the company have been successful and 60 have been unsuccessful. Before the toy is marketed, a market research is conducted and a report either favorable or unfavorable is submitted, is compiled. In the past, 80% of the successful toys received a favorable market research report and 30% of the unsuccessful received a favorable market research report. So, it may be possible that you do a marketing survey. So, it is not 100% that you are able to predict everything. So, even if the marketing survey the data may give you that the market is actually bad, but still it is giving a good set of information to you, or it may be possible the market is good, but still the marketing survey is giving you a bad survey report. So, any combinations are possible, and obviously, other two combinations are the marketing survey does really analyze the market and it is good and it gives you a good report, and it analyzes the market is bad and it gives you a bad report. So, those are actually what it is and you are getting the information, but the other two instances where it is good, but you get a bad report, or it is bad you get a good report, are the problematic area. But and obviously, we will consider such problems later on in the hypothesis testing. So, the marketing manager wants to know the probability that the toy will be successful if it receives a favorable report. So, basically you analyze the market, which one should be B1, which one should be B2, which one should be B3, such that B1, B2, B3 or whatever however different values of n you have, you basically combine them and try to find out that they are mutually exclusive and exhaustive, and solve the problems accordingly. Now, what we will mean by independence of events? Now, here be careful what I mention and note down it very carefully. So, we will say two events are independent if the probability of the intersection of A and B are in events which are in part and parcel of the universal set. So, we will say A and B are mutually independent of each other, taking two at a time if the probability of A intersection B is given by the multiplicative value of probability A into probability B. Now, if I am saying that if there are three events, if they are independent, how would we analyze? It will be given that three events A1, A2, A3 are independent of each other if probability of A1 intersection A2 intersection A3 is given by probability of A1 multiplied by probability A2 multiplied by the probability of A3. So, now further on, now what we will now consider is basically a little bit different. We will consider the different type of distributions, and we will come to the uses of distribution in different general examples. Now, depending on what is the outcome of an experiment, we will basically have a random variable to denote that what is the actual thing we are going to study, what we are going to learn, and we will consider that is to be random, because the fact that we do not know what should the outcome be of the experiment which we are trying to study. So, this random variable which is RV would be used to denote the outcome of an experiment, and we will try to basically denote the random variable by either the capital symbol of the variable x or capital Y or capital Z. Now, the reason why we use capital 1 is basically denotes the random variable which is unknown before we do the experiment or as we are doing the experiment. The moment we complete the experiment, the value which is in front of us is known, it is known as the realized value, and the random variable may take those realized value depending on what is the actual probability function based on which you are trying to map the random variable and the different type of realized value. So, this is basically a mapping where you take a random variable x, put it into the function, that function what we want to find out is the probability distribution function, and the output which we will get would be based on the fact that what capital X takes, that small realized value is small x, based on when you put the small realized value small x into the function, you get an actual functional value which is known as the probability distribution function. So, let us consider a very simple example. Consider a coin and it is an unbiased one. So, there is a head, there is a tail. Consider that rather than head and tail, the coins in one face you have red color, another face you have basically yellow color. Now, so now before you toss or as the coin is tossed in the air, we are interested to find out that what face will come out. So, we will denote the random variable capital X by the face which will mean that we want to study the face which will be coming out on the top, and we know that for that face which is a random variable which we do not know as the experiment is being done, but what we actually know is that once the face actually comes out, they are basically two realized values, one is the red one is the yellow one. Now, you may say that why you are basically trying to depict them as colors, but then how does the value of numbers come into as the probability sense. Now, consider the example that those red and yellow are removed, but you put that in the case of a coin where the faces are now black and white, or you consider the coin is in such a way that the faces in one face there is one dot and in another face there is two dots. So, your actual aim is to find out the outcome, but what you are trying to do is that outcome is mapped onto a function which is basically a mathematical functional formulation which gives us that what is the outcome and what is the corresponding probability based on which we are trying to study that outcome. Now, consider the second example, again the probability example, not of the coin, but of a dice. Consider the faces are marked 1 to 6. So, obviously, this why I am saying 1 to 6 or why I told 1 dot for the coin or 2 dots for the coin is basically to give you an example such that the underlying fact of the experiment which you are trying to do need not have any quantitative values assigned to them, but the actual output based on which we are trying to understand the concept of probability are all quantitative in nature, because they are some functional form such that once the capital X, whether qualitative or quantitative, whatever it is, it takes its realized value. Once you put the realized value into the functional form, you get an output which is in number terms, that is the probability. Now, consider the dice example. If you roll the dice, the probability of getting any face, that is 1 to 6, is given by 1/6. Now, replace that experiment with the same sort of dice, say exact same density, same weight, same shape, whatever it is, same material, but now the faces are marked by the letters A, B, C, D. So, A for 1, B for 2, and so on and so forth. Now, you again do the experiment. In the initial case, the experiment outcomes were dots 1 to 6, any one of them. Now, but now in this second experiment, they are not the dots, but they are the faces are the alphabetic values A, B, C, D, whatever. So, when you are doing the experiment in both the cases, the capital X, the random variable, where in one case the random variable denotes the outcome which is unknown, in the second case also the outcome is unknown. But when actually x takes place and you know that, in the first case small x, which is the realized value, gives us the point which is either 1 or 2 or 3 or 4 or 5 or 6. In the second case, when the realized values comes, they are the value either A or B or C or D or E or F. But the corresponding functional mapping, when you put these values 1 to 6 or A to F into the function f of x, the outcome is the probability which is 1 by 6 in both the cases, provided they are unbiased quant. Now, we will consider that the outcomes which you are doing for the experiment can be either continuous or they can be discrete. So, now you will be asking what do you mean by continuous and discrete? The x values which are the outcomes can be either be discrete or continuous, based on the fact, hence we will have the probability mass function for the case when it is discrete and probability distribution function for the case when they are continuous. So, these would basically given by the functional form of small f of x in both the cases, and we will analyze them in details later on. So, let me continue reading it. So, we will usually denote the random variable using x, y or z, and the corresponding probability will given, as I just mentioned, that by small f of x or small f of y or small f of z. Now, this f of small x, f of small y, f of small z, they are not small f of capital X or not small f of capital Y, because those capital values denote the random variable. Once you plug in the values which is the realized one, that will give you what is actually the PDF or the PMF or the distribution we are trying to consider. Now, if it is a discrete distribution, we will have basically the probability mass function, that means the probabilities are all concentrated on masses, and if it is continuous, it is known as the probability density function, where the random variable which we are trying to understand or trying to study are continuous in nature. Now, let us come back to the example of a probability mass function. This example which we consider, these two examples of a tossing a coin or rolling a die. Now, when you basically roll the die, the probabilities are concentrated at the values of the realized values which are either any one of them, either 1. So, hence the corresponding probability which is being assigned, or the masses which are being assigned to the value 1, and the corresponding probability is 1 by 6. If you come to the example of, say for example, when you are trying to analyze the probability for the realized value as 2, again it is 1 by 6. Where it is 3, it is again 1 by 6, 4 it is again 1 by 6, 5 again 1 by 6, 6 again 1 by 6, which means that the probabilities are concentrated at the values 1 to 6, but any probability values at the point other than 1 to 6 are 0. Now, you may be asking that what does it mean? It does not show such, then when you are trying to plot the value of the CDF, which is the cumulative distribution function. I will come to that later on. But in the case when you are trying to analyze the probability density function, we do not consider the densities are concentrated on only points, and basically analyze that in later on in more details. So, now we will consider the discrete distributions, and what I have talked about, showing that one slide for about 10 minutes. I will go into the details about that discussion later on also. So, the discrete distribution which we will consider for our example in this DADM1 course would be the uniform discrete distribution, the binomial distribution, the negative binomial distribution, the geometric distribution, the hypergeometric distribution, the Poisson distribution, the log distributions, and there are other distributions also which we will not consider in details. These would be more than sufficient to basically at least cover the probability mass function. Now, before we discuss the discrete probability distribution or the PMF, probability mass functions, we will like to basically go into the concept, very simple concept of Bernoulli trials. Now, in the Bernoulli trial, we have basically two outcomes. It can be more than two outcomes also, not for the Bernoulli trials, but for the experiment, but we are not going to go into the details of that. So, there are an experiment or trial which you do, or or some random experiment which you do, and there are two possible outcomes. Say there is a success and a failure. So, that very good example would be a head and a tail, but if you are considering rolling the die, it is not. If and only if you are able to divide the rolling of the die into into even numbers and odd numbers, obviously there are two categories, then it can be said depending on how you have been able to formulate the experiment as Bernoulli trial. But let us not go into such details, but let us come to the simple example. So, each trial of the Bernoulli trial has two possible outcomes, which is a success or a failure, or a head or a tail, or a yes or a no, whatever it is. These trials are independent. That means, when we do the experiment, the outcome of the head or outcome of the yes or outcome of the red or outcome of white, whatever it is, does not affect the complementary event of that. That is, for the yes it is a no, for a head is a tail, for a white is a black, whatever, it does not affect that, and vice versa also. That means, the trials are independent also, which basically means that if I do the experiment repeatedly, like I roll the die and I want to find out the probability of getting a even number or odd number, or the experiment which I do is basically I toss the coin, I want to find out the head or the tail. Now, if I keep doing these tosses, these are each trials, these trials are independent of each other. That means, one trial does not affect the next, or the next trial does not affect the former. So, they are independent of each other. Now, the third point I have already mentioned, it means the probability of a success or a failure remains the same, and it is does not change from experiment to experiment. Now, there are other important point which I also mentioned. Consider that you have a coin and you keep tossing it. So, the trials do not affect each other, they are independent. That was point number 2 as mentioned in the slide. Point number 3 is that the outcome of a head or outcome of a tail, whatever the outcomes are we have denoted in tossing the coin, are independent of each other, do not affect. That means, it is not that if the outcome of the head and the tail for an unbiased coin is half and half, the probability does not change from trial to trial, it remains half, and head does not affect the tail in the next outcome, or head does not affect the head for the last outcome, and or tail does not affect the tail, or tail does not affect the head, and it continues in that way. In case if you have a trial where there are 3 outcomes, the same concept can be utilized, where the trials will be independent of each other, they will be 3 trials, whatever the probabilities are, they can be P1, P2, P3, and the probabilities of getting the first one, which is P1, would not affect P2 or P3, and vice versa, in the sense P2 would not affect P1 and P3, similarly P3 would not affect P1 and P2, and it will continue in this way. So, let us consider the first discrete distribution, which is the uniform discrete case. So, x is the random variable, and we denote as, I am just hovering my pen here, it means ud, which is the uniform discrete distribution, and this a and b are the parameters based on which we are trying to basically find out the uniform discrete distribution case. So, u is uniform, d is discrete, a and b are the parameters. Now, the f of x, which is the PEMF, is denoted by 1 by n is basically a number of such trials which you have, and the realized values of x, which is the random variables, are in the least case you can have basically the minimum value, which is a, and the corresponding masses are concentrated at points which are a plus k. That means, the next jump is basically from a to a plus k. The next jump further on would be a plus k, which is a plus 2 k, and it will go on till the last value, which is b. So, that means, the masses are concentrated at the realized values which are a plus k, a plus 2 k, so on and so forth till b, and there are such n number of such masses where the probabilities can be found out. Here a and b are the parameters which are on the real line. The expected value, I will come to the expected value and the variances concept later on when we solve the problems. So, the and they will be utilized later on also. The expected value is given by a plus k by 2 into n minus 1, and the variance is given by k square into n square minus 1 divided by 12. So, what can be the example? Example can be generating the random numbers 1, 2, 3, 4 till 10. Here the random distribution of the probability mass function will be given by x is uniform distributed between 1 and 10. So, a is 1, b is 10, where the values of k, provided they are only discrete number like 1, 2, 3, 4, in that case a is 1, then a plus k is 2. So, hence k would be 1, and you can find out that what are the different numbers of n's which you have, based on which you can formulate the PMF, which is the probability mass function. You can find out the expected value, you can find out the variance also. Now, remember one thing, for the uniform distribution case, if you are able to draw it, how it will look like, I will come to that later on, and I will also signify the main concept of the expected value. There is a reason for that, and I will come to the variances expected value for the other distributions later on also. So, this is a uniform discrete distribution. I have drew it in very simple Excel. So, the values are of the x's are from 1 to 20. The corresponding probabilities are given by 0.1. So, these are uniform discrete. So, the heights are all equal. So, f of x is plotted along the y axis and x values are plotted along the x axis. And if you find out, the expected value would be the center of gravity of this figure. So, obviously, the expected value would be denoted by somewhere in between. So, this I am just using a very simple concept. So, center gravity, which we know in physics or very simple class 10 or 12 concept of simple sciences. So, center of gravity is basically where you can basically balance it, and the weight would basically be kept balanced. Like if you have a scale of 1 feet, which is 12 inch or 30 centimeters, if you balance it at the point which is 15 centimeters, it will be keep balanced because the weights on the left hand side and the right hand side are equal. So, this is the same way what we denote. So, we will consider now the binomial distribution. So, binomial distribution is given by, if you remember the binomial expansion which we have done in class. So, it is given by basically a plus x to the power n. So, you want to basically expand it. So, the first term would basically be NC0 a to the power n x to the power 0, and the last term would basically be NCn a to the power 0 x to the power n. So, basically you find out all the powers of x and a as they keep changing, such that x increases from 0 to n and simultaneously a basically changes from n to 0, such that the power values when they added up for a and x are always n. Now, here n and p are the parameters and the random variable is x, b is the binomial distribution, the parameters are p and n. Now, p is the probability of the good thing or the bad thing, whatever it is, however you denote, or yes or no. So, if it is p is for yes, then probability of no would be 1 minus p. If p is no, then the probability of yes would be 1 minus p, whatever way you denote. Now, the f of x is given by NCx p to the power x q to the power n minus x, and the x values are from 0 to n. So, x being 0 means the corresponding probability of getting the good item is 0, there is no good items and the values of all the bad items are all the n, and if basically x is n, it means all the good items are there while the number of bad items are 0. So, n and p are the parameters. So, p is between 0 and 1, n is integers positive, expected value is given by n into p, variance is given into n p q. So, consider an example, you are checking the quality of the product coming out from the shop floor. A product can either pass with the probability of 0.8 and fail with probability of 0.2. It can also be the other way around, like you want to find out the probability of the bad items. So, obviously, in that case p is 0.2 and q is 0.8. Now, you are checking 50 such items which n is 50. If x is the random variable which denotes the number of success, then for the inspection of such 50 items it will be 50 C x which is n is 50, p to the power x which is 0.8 to the power x, and q to the power n minus x which is 50 minus x would be given by 0.2 to the power 50 minus x. Now, remember, if you want to find out the bad items, again the formula remains the same, initial part 50 C x would remain the same, it will be 0.2 to the power x and 0.8 to the power 50 minus x, but in that case x is number of bad items, while in this case which is shown on the slide is the number of good items. So, with this I will end this 7th lecture and continue the discussion further on with examples for the binomial distribution, so on and so on and so forth. Have a nice day. Thank you very much.